congruence modulo B is an equivalence relation. For any choice of B, this is an equivalence relation on the set of integers. Okay, and recall, equivalence relation just means you had to show three properties, that it is reflexive, it is symmetric and transitive, and all these three just follow from the original definition that we gave of what congruence was. Okay, so here is the definition, which said that x and y are congruent to each other mod B if they leave the same remainder when divided by B. Okay. So, if you just think about it a little bit, you will see that this property of leaving the same remainder has all those three aspects, the reflexivity, symmetry and the transitivity. Okay. So, I leave this as a simple exercise for you to check that this is an equivalence relation, and when you have an equivalence relation, recall what it does is it splits the set up into disjoint equivalence classes. So, an equivalence class just means you take your set, in this case a set of integers, and then an equivalence class would just be everything that is congruent to each other modulo B. So, maybe this is all things which are congruent to each other modulo B. Each of these subsets has things which are congruent to each other modulo B in this case, because that is a relation, and things in two different classes are not congruent to each other, right. Okay, so this is what the general picture of an equivalence, general picture of equivalence classes looks like. This is how it would split your set up into disjoint subsets, but in our case we actually know what the equivalence classes are. So, if you look, we already drew this table. So, here is the first equivalence class, it is all numbers which are congruent to 0 mod 7, things which leave a remainder of 0. Now, the second column is another equivalence class, 1, 8, 15 etc. So, here is the third equivalence class, 4th, 6 and 7. So, there are 7 equivalence classes, and which are just the columns of that table, and notice that they are all disjoint, they split the set of integers up into these disjoint subsets, and so we of course also thought of them as being arranged on a cylinder, for example.
At what time are you planning to go for lunch?
In 30 minutes from now.
30 minutes from now. Right now it is 12:40, which means that half an hour later we had had lunch at 1:10.
So, what we just did is we added 30, which is the half an hour, to 40. So, here is my clock, but my hour hand has broken off, I do not have it anymore. So, I am just looking at what I can do with the minutes. So, right now it is 40 minutes past the hour, whatever the hour may be, and to that we add a 30, right. So, of course, if you did this on the number line, you would get 40 plus 30 is 70, but we are not doing this on the number line, we are on a clock. So, what does that mean? So, 40 plus 5 is 45 plus 10, therefore it is 50. So, when I add 20 to 40 I get 60, which is 0, and then I add 10 more and I am at the 10-minute mark. So, in a sense 40 plus 30 is 10. Okay. Now, what we are doing here is sort of doing arithmetic with numbers, but we are only keeping track of the remainders that we get when we divide by 60. Okay. So, we have forgotten the hour, we are only remembering what the minutes look like. So, now for instance to 10, if you add let us say another 30, then 10 plus 30 is 40, but well that is just the 40-minute mark, right. So, 10 plus 30 is 40 on a number line, it is also 40 on the clock, but every time you cross the 60-minute mark, then you would get an answer which would be different from what you would get on the number line. So, let us do another one. For instance, what is 40 plus 25? Well, that would be 65 if you did it on the number line, but as you well know, on the clock you are actually at the number 5.
So, can you do this on other kinds of clocks? What if there is some weird planet where the hour has 7 minutes?
Oh, I happen to have exactly such a clock. So, let us do it with that one. So here is a clock which has just got numbers from 0 to 6 on it. In some sense it is a 7-minute clock rather than a 60 minutes on the clock. So let us do addition on this. So which two numbers would you like to add?
4 and 5.
Okay, so let us see how do we add two numbers. We first start, we keep our initial position on the very first number. So we are on the number 4 now, and to this we need to add the number 5. Okay, so I move 5 steps. So 1, 2, 3, 4 and 5. So 4 plus 5 on my clock is 2. Any other pair of numbers you fancy?
Let us try, we are already at 2, so let us try 2 plus 5.
2 plus 5, okay, that is interesting. So 2, and now I need to move 5 steps. So 1, that gives me 3, 2, 3, 4, 5. So 2 plus 5 on my clock is actually a 0. Okay. So what we are doing here is just like we said in the earlier example of 60, we are doing addition like we would on the number line, except we only keep track of what the remainder is in the final answer. We do not care about what the quotient was. So what we just did was what we would call arithmetic, but with congruence classes. So arithmetic with congruences. This just means you do addition, subtraction. So what is arithmetic in general? You do addition, multiplication, subtraction. We will eventually also look at division, but addition and multiplication for now, the two basic operations for us, we sort of want to do them but on a clock, okay, and let us do them on the 7-hour clock that we talked about. So let us do everything modulo 7. So I will take my number b to be 7, and let us do them by example for a start. So for instance, if I took the number, so as we saw 2 plus 5, well, what is that? Well, 2 plus 5 should actually be a 7, right. This is if you did it on the number line, but if you just thought about what remainders you get when you divide them by 7. So 2 gives a remainder of 2, 5 gives a remainder of 5 and 7 gives a remainder of 0. Okay. So if I did this very same addition on the 7-hour clock, then 2 plus 5 is actually a 0 on that clock. Okay, let us do another one. So take larger numbers here. Suppose I try to do 15 plus 11, okay, but now let us do everything modulo 7, meaning we will only keep track of remainders. 15 when divided by 7 is, well, 1, 15, 7 2s are 14 plus 1 is 15. 11 when divided by 7 gives me a remainder of 4. So 15 plus 11, if I just did it on the number line, is a 26, but when I do this on my clock, 26 divided by 7 just gives me 5. Okay. So what are we doing in general here is, in a sense, it is actually enough to just keep track of the remainder. So let me just write this down as a little proposition. It sort of allows us to calculate remainders very fast in various situations. So here is the first statement which says, suppose x and y, x1 and y1 are congruent modulo b, okay, and x2 is congruent to y2 modulo b, then the sum of x1 and x2 is congruent to the sum of y1 and y2 mod b. Then the sum is congruent to the sum, and the product x1 x2 is congruent to the product y1 y2. Okay. So let's prove this. So what it says is that when you want to calculate remainders of say a sum of two numbers mod b, if you know the two individual remainders, then it is enough to just add them up separately. Okay. So, for instance, we did this in this example here. So, if our numbers were 15 and 11, we knew what the remainders were mod b. So, 15 was just 1 mod 7, 11 was congruent to 4 mod 7, 15 plus 11 is 26, but instead of calculating the remainder when you divide 26 by 7, you could have done it faster by just saying, well, I know the two individual remainders, all I will do is I will just add those two up together. So, 1 plus 4 in this case quickly tells me that the answer is 5. So, that is really what the first proposition tells us here. So, let us prove this. The proof is just a simple application. For example, we could do it using our lemma. So, what do we want to prove? So, let us prove the first statement. So, we want to show, if we use our lemma, that the difference between these two numbers x1 plus x2 minus y1 plus y2 is a multiple of b, okay, is a multiple of b. But what we know is the following, that each of those two differences, however, we know the following, that b divides x1 minus y1 and b divides x2 minus y2. Okay, this is because of what is given, x1 congruent to y1, x2 congruent to y2, and so since b divides each of them, it divides their sum. So, it is the same sort of argument that we have used earlier as well. That is what you want, x1 plus x2 minus y1 plus y2. Now, the proof of the second one is a little more interesting, and it is again a similar argument to things that you have used, for example, when studying limits and so on. You want to prove, say, a limit of a product is a product of the limits, things like that. This sort of argument is always used. So, let us see what is it that we want to prove. We want to prove that x1 x2 minus y1 y2 is divisible by b. Now, again we do the following, we sort of add and subtract a suitable term. So, let us add and subtract x1 y2 . Okay. Now, doing this allows us to write this as x1 times x2 minus y2 plus y2 times x1 minus y1. Okay. Now, x2 minus y2 and x1 minus y1 are both multiples of b. So, this is known to be a multiple of b, it is given to be a multiple of b, this is given to be a multiple of b, and therefore, what you have on the right hand side, the overall thing is of course a multiple of b. Okay. So, that is the end of the proof. Okay. So, what does this allow you to do? This little proposition allows you to sort of do arithmetic with congruences very fast. By that we mean, if you want to calculate remainders modulo something, you can just sort of use the products of the remainders. So, let me just give you one example which came up when we were trying to figure out a test for divisibility by 7 and so on. So, we were trying to do this, or when we were talking about Fermat's little theorem, we were saying, what do you get when you take different powers of 10 and you divide them by 7, what are the different remainders you get? So, 10 power n, what can you say about the remainders on division by 7? Okay. So, let us see how to do this quickly using our previous proposition. So, what we know is this, 10 itself is easy to calculate, 10 on division by 7 gives a remainder of 3. So, this we know. Okay. So, 10 is congruent to 3 mod 10. Now, I am interested in finding out what is 10 squared congruent to. In other words, I want to multiply the previous, this I know what 10 is congruent to, I want to multiply 10 by 10, okay, and ask what that number is congruent to. So, we sort of do the following clever thing, well, observe, I can just think of 10 as being congruent to itself mod 7. So, this is, I am not really saying anything new here, 10 of course is congruent to itself mod 7, okay, but why are we sort of inserting that little congruence there? Because now this allows us to use the product rule for congruences that we talked about. So, if I know this, from here I conclude that the product 10 times 10 is congruent to 3 times 10. mod 7. Okay, so my original problem, which was to find out what 10 squared is congruent to, has become a somewhat simpler problem. I have smaller numbers at play. I have to figure out what 3 into 10 is congruent to. Okay, and that is a smaller number, it is 30, and I know 30 mod 7 is 28 is the quotient and 2 is the remainder. So 10 squared is congruent to 2 mod 7. So I conclude that quickly without, see, observe, I did not actually calculate what 10 squared was in this case. Okay. Okay, now we can keep going this way. If I want to figure out what is 10 cubed congruent to, I just take the previous congruence and I sort of attach it, I look at this last one, 10 is congruent to 10. So in other words, I can multiply both sides of the congruence by a 10. So 10 cubed becomes congruent to 10 into 2 mod 7, again by the same logic as before. And now instead of trying to figure out what 1000 is congruent to, I have a much simpler problem. I just have to figure out what 20 is congruent to mod 7, okay, and 20 is of course 6. Okay, so now let us go on, 10 to the 4, I just have to multiply both sides by 10, so that becomes 60 mod 7, which is just 4. 56 is the quotient and 56 is 7 times 8, okay, and so on. So 10 power 5 likewise is 4 tens are 40, and 40 is just 5 mod 7. Okay, and finally the very last step of Fermat's little theorem says 10 to the 6 becomes 5 into 10, which is 50 mod 7, and 50 is just 1 mod 7. So recall, these were the very same numbers that we generated when we were trying to figure out what the various powers of 10 were congruent to. So 10 squared was 2, this was 3, then there was 4, 5, and then finally a 1. Okay. So what we have done here is really computed these numbers in a much simpler fashion by using the rules or the arithmetic of congruences.